Training neural networks requires minimizing a loss function across millions of parameters. This optimization relies on gradient descent, which iteratively adjusts parameters in the direction opposite to the gradient. The gradient is a vector composed of partial derivatives of the loss function with respect to every single parameter. Calculating these millions of derivatives must be instantaneous and exact. Traditional symbolic differentiation generates expressions that explode in complexity for deep networks. Numerical differentiation, using finite differences, introduces unavoidable truncation and round-off errors due to floating-point precision limits. Automatic differentiation bypasses both issues by applying the chain rule algorithmically to the function structure, ensuring precision and computational tractability. This technique is the fundamental engine powering all modern machine learning training. Symbolic differentiation provides mathematically exact derivatives, but fails when the function is defined by complex control flow, such as loops or conditional statements common in procedural code. Numerical differentiation approximates the derivative using the formula f of x plus h minus f of x divided by h. The choice of the step size h is critical. A large h causes truncation error, where the approximation deviates significantly from the true derivative. A small h leads to catastrophic cancellation, where subtracting two nearly equal floating-point numbers results in a large relative error. Automatic differentiation avoids this trade-off entirely because it calculates derivatives based on the function's decomposition, not its numerical behavior or symbolic form.
Automatic differentiation operates by decomposing any complex function into a sequence of elementary operations. These operations include basic arithmetic, exponentiation, and trigonometric functions. This sequence forms a directed acyclic graph, known as the computational graph. Each node in the graph represents an elementary operation, and the edges represent the flow of intermediate values. The derivative of every elementary operation is known analytically. The core principle of AD is the systematic application of the chain rule across this graph. If a function z depends on y and y depends on x, the derivative of z with respect to x is the product of the derivative of z with respect to y and the derivative of y with respect to x. Automatic differentiation can be executed in two primary modes. Forward mode AD calculates the derivative alongside the function evaluation itself. It propagates derivative information, known as the tangent, from the input variables towards the output. For each node in the computational graph, the local derivative is calculated and multiplied by the incoming tangent using the chain rule. This process yields the derivative of the final output with respect to the initial input variable. Forward mode is computationally efficient when the number of input variables is small relative to the number of output variables, such as calculating the Jacobian vector product for sensitivity analysis. Consider a typical deep learning scenario where the loss function L is a single scalar output, but the input vector W, representing the model weights, contains millions of elements. Forward mode AD calculates the derivative with respect to only one input variable per pass. To obtain the full gradient vector, which requires the derivative with respect to all n input variables, the entire forward pass must be repeated n times. If n is in the millions, this repetition makes forward mode computationally infeasible for training large neural networks. This limitation necessitates a different approach for efficient gradient calculation in optimization problems.
Reverse mode automatic differentiation, universally known as backpropagation in deep learning, solves the scaling problem. It is efficient when the number of outputs m is small compared to the number of inputs n. Instead of propagating tangents forward, reverse mode starts at the scalar output, the loss function, and propagates derivative information backward toward the inputs. The derivative of the output with respect to an intermediate variable is called the adjoint. The backward pass calculates the adjoints by traversing the computational graph in reverse order, applying the chain rule at each node, using the stored intermediate values from the forward pass. Reverse mode AD calculates the entire gradient vector in a single backward pass, regardless of the number of input parameters n. This efficiency stems from calculating the Jacobian transpose vector product. The computational cost of the backward pass is proportional to the cost of the forward pass. For a scalar loss function, the total time required to compute the full gradient is typically only 2 to 3 times the time required for the initial forward computation. This linear scaling with respect to the forward computation time, independent of the number of parameters, is the reason reverse mode AD is the only viable method for training massive models. Modern frameworks like PyTorch and TensorFlow implement AD using dynamic computational graphs, often referred to as gradient tapes. During the forward pass, the framework records every tensor operation performed. This recording includes the input tensors, the operation type, and the necessary information to compute the local derivative during the backward pass. When the user requests the gradient, the framework traverses this tape in reverse. It retrieves the stored intermediate values and applies the chain rule using the adjoints, calculating the gradient for all leaf tensors, which are typically the trainable weights. This dynamic approach allows for flexible control flow and conditional execution within the model definition.
PyTorch's autograd system is inherently dynamic, building the graph on the fly during execution. TensorFlow initially relied on static graphs, but now heavily promotes eager execution, which functions similarly to PyTorch's dynamic tape system. Both frameworks automatically manage the memory required to store intermediate values and the resulting gradients. The user defines the forward computation, and the framework automatically generates the corresponding backward computation, based on the principles of reverse-mode automatic differentiation. This abstraction allows researchers and engineers to focus on model architecture while relying on mathematically precise and highly optimized gradient calculation.